Hello everyone. In this video, let us try to graphically understand what we meant by the clock network delays. So basically we said that delta 1 was the launch clock network delay and delta 2 was the capture clock network delay. So what do we exactly mean by the clock network delays? So what happens is, if you see the zero pulse or the rising edge of the clock pulse which was expected to come at time period 0 will not come at time period 0, but it will be shifted by a time period delta 1. And why is that? Because when the clock enters into the network and hits the launch flop clock endpoint, there are two buffers and some wires over here. So it will take an amount of delay that is nothing but delta 1 delay to reach the launch flop clock endpoint. And this is the real scenario. So on a real chip, the clock won't reach exactly at 0, but it will reach at some time after 0, which is delta 1, and that particular delta 1 is nothing but a launch flop clock delay. Okay, similarly you have the same thing for the capture as well. So the capture, if you have delta 2 is nothing but whenever your clock starts from this point, it will take a delay 1 2 3 4, this 3 buffer delays, and plus the wire delay to reach at the capture flop clock endpoint. So the clock period, the second cycle, this was the first rising edge, this is the second rising edge, and the second rising edge will at the capture flop clock endpoint will not appear at t, but it will appear after some time. It will appear at a time delta 2 after t. So t plus delta 2, so this value over here, this it is at this point when the second cycle for the clock will appear. Now the real clock edges that we have initially with the ideal clock tree, the edges were at 0 and t, but now having the real clocks in the picture, the clock edges will now appear not at 0, not at t, but it will appear at 0 plus delta 1 and at t plus delta 2. So that is where actually the clock now appears on a real chip, and hence and hence this analysis is close to a real chip analysis. So now that's why the equation now becomes theta plus delta 1 should be less than t plus delta 2. So if we satisfy this equation, we can very confidently say that this system will be working at 1 nanosecond or at 1 gigahertz. We can say this confidently. So we'll look in in the upcoming slides that what happens when this delta 1 and delta 2 are not equal. So we'll look into that in some time from now, but let us try to conclude on this particular scenario also. So also there is something called as setup time of the capture flop. Setup time of the capture flop is a small amount of time period that is required by the capture flop to recognize the data. So there is a mux that is present over here inside the capture flop, and that mux delay is basically nothing but the setup time s. So this part we have covered in a separate set of videos called as VLSI Academy. In that set of videos we have covered what is the meaning of s and what is the meaning of uncertainty. So we have covered these two part in those videos, so you might want to have a look into those videos. So what happens when you consider these two things, the setup time and the uncertainty, let me try to explain what is uncertainty. So uncertainty is the clock edges. It is very unlikely that the clock edges will appear exactly at the time period that is expected. So 0 plus delta 1 is it is expected to arrive at 0 plus delta 1, but not all the clock edges will come at delta 1. It might come at a time period which is less than delta 1 or which is greater than delta 1. So there is a small window over here. Similarly, there is a small window over here as well. So these things are basically captured or modeled in the form of uncertainty, and the reason that the clock edge might move either on the left side or on the right side, this phenomenon is called as clock jitter, and this part we have very briefly covered in a separate separate section of videos that we call at VLSI Academy. So in those we have covered what is jitter, and that particular part is nothing but what is modeled in the value of uncertainty. So here we have assumed the setup uncertainty as 90 picoseconds and the setup time of the capture flop as 10 picoseconds. So you might want to have a look into the timing setup timing videos in the VLSI Academy lectures that has been again conducted by us. So yeah, so this is how you have to model it. So the equation becomes now close to a real one. so before that, before completing the equation, let us try to find out what is skew. So in this case, the delta 1, the mod of delta 1 minus delta 2 is nothing but the skew, and it is expected to be 0. It is expected to be exactly 0 picoseconds. If this delta 1 is exactly equal to delta 2, then the equation that becomes nothing but close to close to the equation that we looked for an ideal clock, that is theta should be less than t. So in that, if we have taken care of this part delta 1 and delta 2 through the videos that we have been looking in the initial when we started this section, if all those things have been taken care of, the checklist has been filled, and whatever observations we have made, if those things has been taken care of, this particular part, which is delta 1 minus delta 2 is equal to skew, and it should be a 0 picosecond value. That part can be taken care if we do a proper clock tree building and look into the checklist that we have been looking in the past videos. So mod of delta 1 and mod of delta 1 minus delta 2 is the skew, and having a non-zero value of skew, how it will impact the timing, we will look into that part sometime. So first let us try to complete the equation. So right now the equation that we have is theta plus delta 1 should be less than t plus delta 2. So graphically it looks like the edge which comes over here and the edge which comes over here. So basically it says that the combinational delay should lie between these two edges. It is as simple as that. It means that the combinational delay should be within these two edges, and if it exceeds this edge, then we can't say that this system will work at 1 gigahertz. So it should be within this particular period. Okay, that's what that's what this particular thing means graphically. So let us try to complete the equation by putting the setup time, because so this is the setup time that is required by this particular flop. So we have to subtract that amount of time from the complete equation. So some amount of time, some finite amount of time will be required by this particular capture flop to actually capture the data somewhere at the center of the flop. So we have covered this in the timing section of VLSI Academy, so you might want to have a look into that. So that part we have to subtract, because that is a time that is required, and that can't be neglected. So it's a must to have kind of thing. So this part we have to subtract from the equation, and then the next comes the setup uncertainty. So we have to subtract the setup uncertainty value also from the clock period, that is from the clock edge that is coming over here. So the clock edge which comes over here, which is this is the time that we have computed through the clock network delay. Out of that you have to subtract the setup time and the setup uncertainty. So this after subtracting these part, so the window which was from this part to this arrow, now the window has become even shorter. It becomes from this part to this part. So now your theta should actually lie within this range. It should drive from this. It should the data part delay should be within this arrow and this particular thing that you see over here. So your combinational delay should be within this window, and if it is not, if it exceeds it somewhere over here, it shows up as a slack or a violation kind of thing, and we have to make the data part delay. So from an equation point of view, it looks something like this, that the theta plus delta 1 should be less than t plus delta 2 minus setup uncertainty. But from a conceptual, from a graphical point of view, it says that the combinational delay should lie between this and this window. That's what this particular equation means by this particular equation means graphically. Okay, so this part we have to meet, and this is the part that we have to take care of, and this is basically a setup timing. We can say that this is a setup timing analysis with real clocks. So this part of the right hand side of the equation is called as the data required time, and the left hand side of the equation is called as the data arrival time. So the naming convention is quite simple. It says data arrival time, which means the data will arrive at D point after this combinational delay, which is theta, plus the clock network delay, which is this one. Okay, that is basically basically the definition of the data arrival time. Data required time on the other hand says that the time period that is required for the data to come, it should be T, which is your time period, plus delta 2, which is your clock network delay, and minus the fixed time that is required, that we can't be neglected, that is the setup time, and that is the setup time of this capture flop, and the setup uncertainty because of the jitter factor. So these two factors has to be subtracted from the clock period plus the clock network delay. So what does data required time says, that the data is required to arrive at this time period. The arrival time says that data is arriving at this time period. So this gives us this is dynamic. The data arrival time is dynamic, and this part becomes static after you do a clock tree synthesis. After the clock tree synthesis has been done, the CTS or the clock tree has been built, this part becomes fixed. So throughout the complete analysis, this is the part that we have to meet, that is data required term. It means it is basically it says that you are required to come at 7 o'clock to the party. You are required to come at 7 o'clock at the party. The data arrival time, it says that you have arrived at the party at 6:30 p.m. or at 6:45 p.m. If you arrive at 7:15 p.m., you are creating a slack of 15 minutes. So that's what it says. So basically a slack of 15 minutes, that means is that there is a violation that you have, there is a rule that you have broken, and the rule should be that you should be there in the party by 7 p.m. but you're arriving at 7:15 p.m. You're late by 15 minutes. It's as simple as that. You are being called in a party at 7 p.m. but you're coming at 7:15 p.m. So 15 minutes is the time that you're late. You're late by 15 minutes. So basically that 15 minutes, it says that that is your slack. That is the violation. That's the slack, that there is a slack of 15 minutes in your arrival time, the time at which you have arrived. It's basically as simple as that. So what we'll do is we'll stop over here since I'm already running out of time, and we'll take from this point onwards and try to arrive at some conclusion that why this delta 1 and delta 2 things becomes important in this particular equation. So let us try to look into all this in the next video. Thank you.